the unknown has always been a tremendous challenge to man. We look with awe at the stars and wonder if we will ever reach them. We marvel at the miracles held in a single drop of blood. Yes, the same quest for knowledge that points us towards the magnitude of the cosmos also leads us to the infinitesimally small. Man has always wanted to probe deeper into the smallness of things. It has been part of his great curiosity about matter itself. Since antiquity, scientists have been striving to find the elementary particles of matter, the basic building blocks of everything around us. The ancient Greeks even gave a name to what they thought of as the basis of all matter. The atom, they called it, meaning something that is indivisible. They never dreamed that the fantastically tiny atom contains a complex world of its own. The optical microscope makes it possible to see a living cell consisting of millions of atoms. The electron microscope takes us deeper into matter, and we may see a virus composed of thousands of atoms. But if we want to delve beyond the limits of the microscope in the search for the atom itself, then we must use powerful new tools and instruments. The particle accelerators, known popularly as atom smashers. Let's go into the control room of an atom smasher. What is an atom? How do we know that it too has parts? How can we see it, smash it, identify its components? We know today that there are at least 103 elements. It is the combination of 92 of these elements into molecules that accounts for all the compounds that are common to our experience from A to Z, from aspirin to zinc oxide salve. But every element has its own atomic structure. An atom is something like a tiny solar system with a nucleus of electrically neutral neutrons and the electrically positive protons. For every proton in the nucleus, there is always a planetary electron. Electrons are electrically negative and so light that it would take 1,840 of them to equal the weight of a single proton or neutron. Despite its small size, the atom is mainly empty space. If an atom were expanded to the size of the giant Dodger Stadium, the tiny nucleus would be about the size of a housefly. The number of electrons and their flight path around the central nucleus determines the chemical properties of the atom of the particular element. So the 103 elements are not really the elementary building blocks of matter. Within their atoms are nuclei, and around these nuclei are orbiting electrons. Every element has its own specific number of electrons. But the discovery of the structure of the atom didn't satisfy the scientists either. Following the atom smashing of the early 1900s, scientists started chipping away at the tiny nucleus. This period of scientific study was capped by discovery of nuclear fission, or splitting of the nucleus, the keystone to all future atomic progress. Breaking open the nucleus with a so-called atom smasher made it possible, in effect, to see and study the atomic nucleus. With the newer accelerators in the 1950s, smashing the particles in the nucleus became possible, and physicists began to learn about the dozens of new elementary or nuclear particles. We use the word see loosely, for man may never really see an atom, let alone its nucleus or the subnuclear particles. But we can recognize and study the nuclear and subnuclear particles by their tracks. A bubble chamber with a camera is designed to make these tracks show up. It is one of the most amazing research tools of all time. The incredibly small elementary particles are produced by electrons or protons accelerated to incredibly high energies by these machines. Hence the terms elementary particle physics or high energy physics. The tinier the particles of matter, the bigger the machines needed to probe them. Because the further we delve into the sub-levels of nuclear structure, the more powerful are the forces of energy, binding together the subnuclear particles. Let's look at the atom smasher, its basic components, its way of operation. It takes a diamond to cut another diamond. Also, it takes an atom to smash another atom. This is the theory of the atom smasher. The process has many things in common with the firing of a cannon. There is a barrel, a projectile, a charge, a target, and an observation post. The projectiles of an atom smasher are particles of the atom. For example, protons or electrons. It is necessary to separate the projectile particles from their atoms if they are to be used as bullets. Electrons are gathered from a hot wire as in a radio tube. Protons are obtained when the electron is stripped from the atom of hydrogen. The hydrogen nucleus is a proton. Now that we have the projectile, we have to find ways to shoot it. The atom smasher or particle accelerator uses electromagnetic attraction and repulsion in the place of powder. Charged particles are repelled by the like electrical charge and attracted by the opposite charge. The energy depends on the nature and amount of the electrical charge or the strength of the magnetic field. The common unit for energy is the electron volt. It corresponds to the energy acquired by one electron charge passing through an electrical potential difference of 1 volt, a unit of energy comparable to the foot-pound. Light atom artillery produces particles with thousands of electron volts. Medium artillery, particles with millions. Heavy atom artillery, particles with billions of electron volts. The accelerated particles, or bullets, need a barrel to give them direction towards the target. Atom smashers use different sorts of barrels to propel or accelerate the particles. This acceleration process gave atom smashers the name accelerators. The atomic bullets may be shot in a straight line or within a circular chamber. In a linear atom smasher, the acceleration may be accomplished within a single acceleration chamber, as in this Van de Graaff unit, or in this Cockcroft-Walton accelerator. The machines bear the names of their inventors. Or the acceleration may be accomplished in a number of consecutive sections. This is the 2-mile-long linear accelerator at Stanford, the largest of its kind in the world. It houses an absolutely straight 2-mile-long copper tube with a diameter of only 4 inches. The projectiles are electrons. During their 2-mile trip from the injection area to the target stations, they are accelerated to an energy of as much as 20 billion electron volts. At the far end of the accelerator, another 1,000 feet is used by a beam switchyard, which directs the electrons into selected target areas. A different acceleration method is employed in the cyclotron, the invention of the late Dr. Ernest O. Lawrence, founder of the radiation laboratory at Berkeley, pointing to the 4-inch acceleration chambers of his original cyclotron. A charged particle in motion is influenced by a magnetic field. This field will bend negatively charged particles in one direction, positively charged particles in the opposite direction. This fact made the cyclotron and more advanced accelerators possible. In a cyclotron, the atomic bullets are inserted in the center and exposed to 2 powerful forces: a magnetic field from 2 mighty magnets and a rapidly alternating electrical force. The particles gain speed and travel in an ever-widening circle until they near the outer edge. Here they are drawn out of the chamber by a deflector and emerge as a beam of high-energy atomic projectiles. In other circular accelerators, the atomic bullets speed around as on a racetrack. They are held in place by powerful magnets and are pushed and pulled by radio frequency electrical forces until they almost reach the speed of light, 186,000 miles a second, the speed limit of the universe. These accelerators are exemplified by the Bevatron at the Lawrence Radiation Laboratory on the West Coast, which develops 6 billion electron volts, by the giant 33 billion electron volt synchrotron, the AGS, at Brookhaven National Laboratory on Long Island, an atomic racetrack 1/4 mile across, the highest energy accelerator in the world. And in the planning stage is this 200 billion electron volts monster, 1 mile across, 3 miles around, a $300 million project. These giant atom smashers need a smaller accelerator as a starter to give the atomic bullets their initial push. The atom smashers produce a stream of high-speed projectiles, which consequently are tremendously powerful projectiles. This barrage is aimed towards targets, the nuclei of other atoms. The ultimate targets, atomic nuclei, may be in a stack of photographic film, in a metal disc, or consist of the atoms of hydrogen in a liquid hydrogen bubble chamber, a giant piece of equipment answering to this colloquial term. All the tremendous effort that goes into an experiment is expended in the hope that one of the millions of atomic bullets may hit one of the millions of target atoms. Should that happen, the observation posts will be on the lookout for new types of tracks that may lead to the discovery of another elementary particle or a better understanding of the basic structure of matter. Photographic plates which have been bombarded by particles are being analyzed for such tracks. The bubble chamber, such as this movable 72-inch unit at Berkeley, is now becoming one of the most successful observation posts. It contains liquid hydrogen, The smashing of a hydrogen nucleus will leave tracks in the liquid hydrogen and reveal this strange world of invisible ammunition and invisible targets. The tracks are like the vapor trails of jet planes. The vapor trails reveal the presence of an aircraft that is otherwise invisible. A camera keeps a continuous record of the activities inside the bubble chamber. Many thousands of exposures from the camera are examined in the search for new, elusive bits of information. What is the purpose of these multi-million-dollar projects? Atom smashers already find many practical applications. They produce radioactive isotopes, atomic tracers used in industry and medicine. Their powerful beam may be used to fight cancer in this painless and bloodless operation with what has been called the atomic knife. But most atom smashers serve pure research. They continue our search for information, the search for new elementary splinters of the unknown, the search for the powerful cosmic glue that holds all matter together. By using atom smashers, scientists someday may learn the mysteries of the basic nature of matter and the laws that govern our universe through the magic of the atom.